So today, under our multiple integrals, we said we are going to go through change of variables in multiple integrals. Now, you can be having a region R, which you might not come out with a single integral using the same region, whether you are doing dx dy or dy dx. Now, in that order, the region might be, if you have to put under dx dy or dy dx, then you are going to maybe split your integrals maybe into 2 or into 3 double integrals. And to prevent us from having many integrals to be evaluated, we can opt and see whether we can change our variables. We put x in terms of u and v, and we put y in terms also of u and v. So by doing so, we are transforming the region so that we will only use one double integral in our evaluation. So we are transforming our region R into a region S. S here just stands for transforming. We are transforming, and we are now coming from region R to region S. The region S will be different from region R, and this will be after the transformation done to region R. Now, this particular dxy all over duv is known as the Jacobian of the transformation, because we are trying to change our variables from one set to another set. Then there must be something that will come out as we change our variable, and that is we will multiply the du dv with the Jacobian of the transformation. And what we normally multiply with is absolute value of the Jacobian. Now, this Jacobian of the transformation is evaluated as follows. It is a determinant of a 2 by 2 matrices. That is when we are dealing with a function of two variables, x and y, which will be changed into a function of two variables, u and v. So dxy all over duv will be equal to dx du, dx dv here, dy du, dy dv. These are partial derivatives. And then we get the determinant of that matrix so formed. After getting the determinant, we only pick the absolute value. That is what we are going to input, where there is the Jacobian in our double integral. Also, if we move to triple integral, our triple integral can also be changed from a function of x, y, z, to a function of u, v, w. So this one can also be done as follows. So for change of variables in triple integrals, we are changing x, y, and z in terms of u, v, w. So the x will be a function of u, v, w, y a function of u, v, w, z a function of u, v, w. Now, because we are transforming from solid K to solid T, we are now going also to have something for the change of variables. So this Jacobian will be used to multiply du, dv, dw because of the change of the variables. Now, the Jacobian will now be a determinant of a 3 by 3 matrices, a 3 by 3 matrix created by these particular differentials, which are partial derivatives, So we can now have an example, one on a double integral, another one on a triple integral, and maybe do other exercises. We can start by an exercise involving getting a Jacobian of a transformation. So, example 1. So, example 1, evaluate this double integral where R is the region bounded by y is equal to 2x plus 1, y is equal to 2x plus 3, y is equal to 2 minus x, y is equal to, and y is equals to 4 minus x. In our solution in such a question, we should always be starting by sketching the region. So we are sketching one, the region. Now, as we can see here, this is our region R, bounded by the said lines. This is the graph, y is equals to 2x plus 1. And this one is y is equals to 2x plus 1. This other one is y is equals to 2x plus 3. And this other one is equals to y is equals to 4 minus x. And this one is equals to y is equals to 2 minus x. Now from this region, if you try to draw a line parallel to y-axis, that line will not be entering that region throughout from one graph and leaving one another same graph. So that one is not happening. It will mean we'll have to divide this particular region maybe into 3 for us to work on the same. So instead of doing that, we can now opt for a change of variable. Or a line drawn parallel to x-axis, we can also not be able to have only one integral will create more than one integral, maybe 2 or 3. As we can see from this section, if you draw a line here, that will be one section. When you come here, it's another section. When you come down there, it's another section. So instead of splitting the integrals into 3, we can do a transformation to this region so that we may only use one double integral. So we'll do a transformation in such a way that we are now moving from XY plane to UV plane. So we want to do a transformation to this particular region into region S. Now we can say, let U be equal to y minus 2x, and v be equal to x plus y, and v be equal to x plus y. If this is the case, therefore we are saying this implies our u then, our new region, u will be equal to 1. U will be equal to 3. V will be equal to 2. And V equal to 4. And V equal to 4. So our new region will now be bounded by U is equal to 1, U is equal to 3, V is equal to 2, and V is equal to 4. So from here, we have known our region, and you can see now the U's and V are having constant values. So getting limits from that, it will now be, this region will be transformed to a rectangle which is parallel to U and V axis, from which taking out limits from that region becomes simpler. Now, we need to go for the Jacobian. From this particular indication, from here we now say, we put in matrix form, we can say this one is equals to minus 2, 1. That is here minus 2, 1, multiplying x and y. This is for this. And here we have 1x plus 1y gives us what? This will give us, the first one is giving us our u. The second one is giving us our v. So from this we can get x and y in terms of u and v. Now, this one will give us, for us to get x and y, we use the method of using an inverse of a matrix. Inverse of this matrix. Inverse of this matrix will be given by minus 1 over the determinant, which is 1 all over minus 2 minus 1. 1 all over the determinant. Minus 2 minus 1. This one now multiplying 1, negative 1, negative 1, negative 2. Now this one multiplying u, v, which will be equal to negative 1 all over 3 into u minus v into minus u minus 2v, which will be equal to just a third into v minus u plus 2v. That is x, y. This implies what? Our x. This implies our x is equals to a third into v minus u. And our y is equals to a third into u plus 2v. Into u plus 2v. U plus 2v. Now from this now, we can now get the Jacobian. The Jacobian will be equal to dxy all over d uv, which will be equal to, we get the determinant, we are getting the determinant of x is equal to this. Now, dx du is minus a third. Dx du is minus a third. Dx dv is positive a third. Dy du is a third. Is a third. And the dy dv is 2/3. Dy dv is 2/3. So we get the Jacobian from here. The determinant of this is minus 2 all over 9 minus 1 all over 9, which gives us minus a third. Which gives us minus a third. Therefore, the absolute value of the Jacobian, what we are going to use, will now be equal to 1 over 3. The absolute value of the Jacobian. Now from this, we need now to draw our transformed region. Our transformed region in our UV plane, and that is V, this is U. So we have U is equals to 1. U is equals to 1 is that line. Here is 1. We have U is equals to 3. This is a straight line passing here. So there is 3. We have V is equals to 2. Let's say there is 2. So that is V is equals to 2. And we have V is equals to 4. So let's say this is 4. So this is V is equals to 4. V is equals to 2. U is equals to 1. And U is equals to 3. So this is now our new region. And as you can see, it's a very good region, a rectangular region parallel to one of the axes. So this is now our region S. That is our region S. Now we are ready to proceed with our evaluation. So the double integral r to xy dy dx will now be equal to double integral. Region is now region S to our x is what? A third into v minus u. That is our x. Our y is a third into u plus 2v. So we have put the value of x and y. Now we are going to follow it with the Jacobian, the absolute value of the Jacobian. That was 2xy, followed by the Jacobian, which is a third. The absolute value of the Jacobian, which is just a third. So this a third was Jacobian. Now we put a du, a dv. Now this one, when it is evaluated, we want to put limits. Now we insert our limits. Now 2 over 3 times a third times another third is 2 all over 27. 2 all over 27 and 2 uv 2v squared. We'll be having 2v squared minus uv minus uv here. Then we have minus u squared. V squared minus u squared minus 2uv. So minus uv. Then we have here du dv. So our u changes from 1 to 3. Our v changes from 2 to 4. Now when we evaluate this, now integrating first with respect to u, and then later we'll integrate with respect to v. So this will be equal to 2 all over 27. The integral from 2 to 4. 2v squared will be 2 all over 3v cubed. Now we are integrating first with respect to u. So it will be 2uv squared. Now this one will be, when you integrate uv with respect to u, it's u squared all over 2v minus now u cubed all over 3 when you integrate u squared. And then we put limits from 1 to 3. Then we have here, we remain with the dv, which will be equal to 2 all over 27 from 2 to 4. From 2 to 4. We are now inserting limits for u, which will be 6v squared. We input 3 here. We input 3 here, we get minus 9 all over 2v. We input 3 here, we get minus 9. We get minus 9. We are putting lower limit. It will be minus 2v squared. We insert here for u lower limit. It will be plus a half v. We put for lower limit here, will be plus a third. Plus a third. The whole of this integrated with respect to v. This one will again give us now 2 all over 27. 2 all over 27. The integral from 2 to 4. 2 to 4, we have 4v squared. 4v squared minus 4v minus 26 all over 3. minus 26 all over minus 26 all over 3. Then we have here dv, which is equals to 2 all over 27. When we integrate further with respect to v, we get 4 all over 3 v cubed minus 2v squared minus 2v squared, then minus 26 all over 3v. We put limits from 2 to 4, which is equals to 2 all over 27 and 2. 4 cubed. That's 256 all over 3 minus 32 minus 108 minus 104 minus 32 over 3 plus 8 plus 8 plus 52 all over 3. So this is 2 all over 27 and 2. We can simplify and this one a bit. This is 224. 224 over 3. This is minus 24. Mm. 200. So this is minus 136 over 3, which comes to 200 all over 81. And that is the answer to that double integral after changing the variables. After changing the variables. So in our example 2, we say determine the volume of this ellipsoid x squared over 25 plus y squared over 16 plus z squared over 9 is equal to 1 using triple integral. So as we can see in this particular expression, ellipsoid is not one of the regular solids, but ellipsoid can be transformed into a sphere by having some form. We can do something so that we transform our ellipsoid into a sphere. So in our solution, we are going to say, we can say let u be equal to x all over 5. Let v be equal to y all over 3. And let w be equal to z all over, just a minute. Let y be equal to, let v be equal to y all over 4. W be equal to z all over 3. This implies what? Our x is equals to 5u. Our y is equals to 4v. And our z is equal to 3w. Now, since u is equal to x all over 5, the solid for integration, the solid of integration will now be the solid of integration will now be u squared plus v squared plus w squared is equals to 1, which is now a sphere of radius 1. A sphere of radius 1. When we have a sphere of radius 1, we have now transformed it to a sphere. From the sphere, now we can convert these coordinates into spherical coordinates as we analyze or evaluate our triple integral. Next now, we need the Jacobian of the transformation. So our J will be equal to dx du 5, dx dv 0, dx dw 0, dy du 0, dy dv 4, dy dw 0, dz du 0, dz dv 0, dz dw 3, which is equal to, if we go for this, the determinant will be equal to 5 into 12, which is just equal to 16. That is, our J is equals to 16. J is equals to 16. Therefore, volume of the ellipsoid first, it is just equal to this. We pick limits from region Q, then we get dz dy dx, which will now be equal to a triple integral, a new solid region, solid T now. This dy, dz dy dx will now be equal to J, absolute value, du, dv, dw, which will be equal to our T is a sphere. Our T is a sphere, so we convert everything into spherical coordinates. So the J here was 60. Since our J was 60, now we say du, dv, dw will now be equal to rho squared sine phi d rho d theta d phi. We are now converting the Cartesian coordinates into spherical coordinates. And now for a full sphere, we know very well, if it is a sphere of radius 1, rho will be changing from 0 to 1. theta will be changing from 0 to 2 pi. And phi will be changing from 0 to pi, which will be equal to 0 to pi, 0 to 2 pi. Now we are integrating with respect to rho. So it will be 20 rho cubed. 20 rho cubed sine phi. And then we put from 0 to 1 d theta d phi, which will be equal to 0 to pi, 0 to 2 pi, 0 to 2 pi. This will just be 20 sine phi. 20 sine phi d theta d phi. So when we integrate further, we are integrating with respect to theta, so we'll have 0 to pi. We have 20 theta sine phi. Then we put limits from 0 to 2 pi, then we remain with the d phi, which will be equal to 0 to pi. We insert that, we get 40 pi sine phi. 40 phi sine phi, then d phi. When we integrate this, we get minus 40 pi cos phi. And we put limits from 0 to pi, which is equals to minus 40 pi into minus 1 minus 1. So the answer is 80 pi cubic units. 80 pi cubic units. And that is the volume of that particular ellipsoid. We can now again have another example. So in our example 3, we say show that the Jacobian of the transformation from Cartesian to polar coordinates is R. So in our solution, we are only showing. So we say x is equal to r cos theta. Y is equals to r sin theta. So J will be equal to dxy dr theta, which will be equal to dx dr dx d theta dy dr and dy d theta. Then we go for the determinant of that particular matrix, which will be equal to determinant of what? dx dr we have cos theta. And dx d theta we have minus r sin theta. dy dr we have sin theta. And dy d theta is r cos theta, which will be equal to r cos squared theta plus r sine squared theta, which is equals to r into cos squared theta plus sine squared theta, which is just equals to r. Since cos squared theta plus sine squared theta is equals to 1. That's the Jacobian of that particular transformation. For change of variables, we can stop there, and somebody can also show that the Jacobian of the transformation from Cartesian to spherical coordinates is equal to rho squared sine phi. Somebody can also show that. So as a matter of maybe practice, somebody may try that to show that the Jacobian of the transformation from Cartesian to spherical coordinates is given by rho squared sine phi.